Hi guys, all right, we've got our last section today, which is going to be all about logarithms. If you are following along in the book, I'm kind of taking pieces from the book in a few different sections just to talk about the main parts that we'll need in order to solve the exponential equations we've been looking at, okay? So you'll see here that if you're following along in the book, we've got 4.6, 6.1, and 6.2 that all cover the topic we're going to cover today, okay? All right, so as far as the logarithmic form goes, so logarithms are the function, are the tool that we're going to be able to use in order to solve for that variable if it's trapped in an exponent. So first of all, we have to understand what a logarithm is. So a logarithm, which often we just call a log, is a function, and it has a base, b, kind of like an exponent has a base. So the logarithm's base is called b, and we write that logarithm log, and that base is a little subscript next to the log. And it's of a, kind of like we have a function of a, so this would be the logarithm base b of a that we're seeing right here. That is the exponent. So that means that here x now is the exponent needed to produce that whatever we're taking the logarithm of. So these two things are the same. So this is your key here, right? That's a lot of words. We're used to seeing b to the x equals a. That's the exact same thing as log base b of a equals x. See what we've switched around here. The bases are still the same. The base of the exponent is the base of the log. It's just that what this exponential term is equal to is now what we're going to take the logarithm of, and the exponent is now what the logarithm is actually equal to. So one good way to remember that is to remember that logs are exponents. So the log is x, that means the exponent is x. Okay, so the first thing we're going to do is just get used to these logarithms, because I feel like that's the hardest part. Every time I teach logarithms, even when I learn them, right, the hardest part is just to understand what this kind of new funky equation actually means. So we're just going to go back and forth between these forms because we are used to this exponential form we see here. So as we look at these next equations, we see a bunch of exponential equations, and all I want you to do is convert them to their other form, to their logarithmic form, okay? So here we see the base of our exponent is 10. So that means we're taking here the log base 10, because that's the base of our exponent. The exponential term, right, the a comes from what the exponential term equals. So the log base 10 of 1,000 is the exponent, right? The logarithm is the exponent. So the exponent is always what we have by itself on the right-hand side. So these two things are equivalent. This is the exponential form here. This is the logarithmic form here. So see if you can't switch the next equation around. The base of the exponent is log base 4, since the base of the exponent is 4. We are taking the logarithm, and it's kind of just this spiral thing too. That's kind of another good way to realize how we're switching this exponential term to a logarithmic term. So log base 4 of what the exponential equation equals. So log base 4 of 0.0625 is the exponent we need, which is -2. Okay, so now when you see logarithmic forms, you can say, okay, that's really funky, but I know it's actually just an exponential equation. It's just a new way right now to write it so that our exponent is actually dropped down from being an actual exponent. We're going to learn how to deal with these logs and simplify these logs by the end of this section so that they actually make sense in helping us solve these exponential equations. Okay, so now just see if you can go the other way around. See if you have this down. So now you see this funky language, log base 10 of 100 equals 2. What are we actually saying there? We're saying that the base 10 to the exponent 2 is 100, which is a true statement, right? Now that makes sense. We know 10 squared is 100. On the next one, see if you can get the right exponential form of this logarithmic equation. Did you get 3 to the -2 equals 1/9? And we know that's right because 3 to the -2 is the same thing as 1/3 squared, and that is 1/9. So these exponential terms, we know those are true, we're good to go. That's what the logarithmic equations are saying as well, just in a new way. Okay, so that's how we switch back and forth. We do that first to start to understand logarithms. Now, we won't always have these equations, right? Because we're trying to solve these exponential equations. So for instance, let's figure out how we would calculate a logarithm. And we're going to do that again by using this switch back and forth from logarithmic to exponential terms. We're going to start that way. Okay, so here I say log base 10 of 1,000,000. I want to know what that equals. Well, I don't know what it equals, so let's set it equal to x because that's what I'm trying to figure out, and then just switch it to exponential form so we can actually understand what we're being asked here. So that means I'm looking for, right, the logarithm. If I'm looking for the logarithm, I'm looking for the exponent. I'm looking for what exponent gives me 1,000,000 when I take 10 to an exponent. And there we just look at the exponents that we know 10 can be, test them in our calculator, but this is one you should maybe recognize. That means that x would have to be 6. 10 to the 6th is 1,000,000. So that means, right, x was what? That means that log base 10 of 1,000,000 is asking us, right, a logarithm is asking for the exponent. It's asking us what exponent do I need to take this base to in order to get this answer. I need to take 10 to the 6th power in order to get 1,000,000. Okay, we're going to do that a couple more times to see if we've got it. So again, this one, what is it asking? It's asking us what exponent do I need to take that base to in order to get what I'm taking the logarithm of? What power do you need to take 2 to in order to get 32? You should get x equals 5 here, meaning that this logarithm equals 5. 2 to the 5th is 32. What about log base 5 of 1/25? Rewrite it again. That means I'm looking for the exponent. 5 to what exponent would give me 1/25? Did you get that one? That one should be a -2, right? Because we know 5 squared is 25, but 5 to the -2 would be 1/5 squared, which is 1/25. So we need that -2 in our exponent in order for the base 5 to become 1/25. Again, just getting a feel for logarithms and what they are here. What if we need to evaluate? We saw this E, right, come about when we were talking about continuous interest. It's a very common base because it is a continuous growth, okay? It's that continuous exponential growth. So you'll see E's come up with logarithms. So what about this one? Just because you see an E, don't get scared. That base is E, right? It's the base of the log right there. And we want to know what exponent we need to take the base to in order to get what we're taking the logarithm of, which is e cubed. Well, right there, we can say, right, I need an exponent of 3 on e to get e cubed. So this answer here, log base e of e cubed, must be 3. You're looking for the exponent when you're asked about the log. A logarithm is an exponent. Okay? Now, a couple things to note here. I have a couple in here that are actually written kind of funny based on how they're normally written. Log base e, I talked about how e was a common base there. Log base e and log base 10 are actually going to be written in slightly different ways because they're so common. 10 is very common because our number system is base 10. Okay, so logarithms base 10 are called common logarithms. And what we do is instead of writing that 10 as a base, It's so common that that has become just log without a base written. So on your calculator, when you see the log key, it is log base 10. Okay, so most of the time we're going to take log base 10. The other log key that you'll see in your calculator is a log base e. So before I wrote that is logarithm base e, that's our natural logarithm. It's naturally occurring in nature. This e comes up naturally. That's kind of where the natural logarithm comes into play. And so if you see this completely different now looking, right, logarithm ln, it just means log base e. Okay, so these two are the most common that we'll see and the only ones that we can evaluate directly in our calculator. So the logarithms will always take so that we can evaluate them in our calculator. Okay, because all the ones I had here, right, of different bases, log base 2, log base 5, were very carefully picked so that I knew what 2 to a power was to get that 32. I knew 5, I could take it to an easy power to get 1 over 25. So we're going to need these common logarithms here, or these natural logarithms, to answer questions like, hey, what about 10? What exponent do I need there in order to get an output of 11? Now, this is where it's going to be helpful because I don't readily know what that exponent should be there, right? I don't know 10 to what power equals 11. It's not a common power of 10, right? 11 isn't. So this is where we need to switch it back to logarithmic form. So your first goal here is to switch this equation into logarithmic form. If you do that, you have log base 10, which remember log base 10 leaves off the 10. Okay, so I have log base 10 written right now. 10 of what the exponential equation equals. So log of 11 equals the exponent, right? The exponent always is by itself on the right-hand side of a logarithmic equation. Now this right here is something I can plug directly into my calculator, log of 11. So grab your calculator and find that log key, not ln, but log specifically, because remember it was base 10 specifically for this equation, and you'll know what x is. If you just plug that into your calculator, you will get a decimal that goes on for a while, but you will get about 1.041. So think about what that means. It means that 10 to about the 1.041 will give us 11, right? 11 is only slightly bigger than 10, so we only need a power slightly bigger than 1 here to get to 11 if our base is 10. Okay, but this right here would be our answer to this equation. And we start to see how we can use already these logarithms to solve for our variable that is in the exponent. Okay, we've done our first one, solving for that variable in the exponent, actually using those logs in the calculator. Now let's do it again. We can do it with exponents that are different from just an x. The entire exponent is what the logarithm equals. So when we change this one to logarithmic form, we still have a base of 10 here. That is still the base of my exponent. So I'm taking a log. I'm taking it of what the exponential equation equals. So log of 100 equals the entire exponent, equals x minus 5. So we can bring down more complicated exponents with logs. It's fine. The logarithm is still the exponent no matter how complicated it is. Now here, this is one we could evaluate by switching it back to exponential form and doing all of those things, okay? But log of 100, you can plug it into your calculator and you'll see that you'll get 2 because 10 squared is 100. And now we can still solve for x, right? It's just solving a linear equation now once we figure out what this number is, evaluating it in our calculator. Okay, so now our final step to solve for x is just to add 5 to both sides, and we see that we need an x equal to 7 here. And that makes sense. 10 to the 7 minus 2 would be 10 squared, and that would give us 100. But we have solved for that x by using logarithmic form, by using logs in our calculator. Okay, here's one where we have a base e. So this is where we would switch this into the logarithmic form using ln, right? Because our base of our log needs to be e, which means that we're looking at ln. We're looking at ln of what the exponential term equals. So ln of 7 equals 3x minus 1. Now I like this example because this logarithm here simplified easily to 2. This ln of 7, when you plug it into your calculator, is not going to do that. So we don't want to round too early, okay? So let me kind of take this over here so we can see what we're doing. So far we have ln of 7 equals 3x minus 1, okay? Let's focus in on that. So don't simplify that yet. Go ahead, and you know this is a number, so you just have to remember in your mind that that's a number, that ln is just a log. And go ahead and add 1 to each side to start solving for x, and just leave that as is until the end. So we have a number plus 1 equals 3x, and we then need to divide by 3 in order to solve this equation. Now is when you should plug this into your calculator. Take the ln of 7, add 1 to it, and then divide that entire number by 3. The one thing here too is if you're plugging this into your calculator, put parentheses around that numerator so you make sure you divide that entire numerator by 3. When you do that, and I would grab a calculator and make sure you get this correct answer, you should get about 0.98197. That's the number we need to plug in for x into this original equation in order to get a power of e that equals 7. Okay? Now, again, these were great, but they all had bases of 10 or e, so we could use our calculator. So the question now is, well, what if I have a base, right? We've been working with all different kinds of bases with these growth factors and decay factors and equations that are not 10 and that are not e. So what we need is a property of logarithms that works really well to help us solve any base of an exponential, solve for any variable in the exponent with any base. And that property is that if you take the logarithm of an exponential term, once you do that, the exponent drops out front, and this becomes x times log of only the base left over. And so what that has done, the logarithm itself has taken the exponent down from being an exponent. Now it's just a multiple sitting out front, and this is just a number that we can evaluate in our calculator, because we can take the log of any base and this will occur. So we're going to take the log base 10 or the log base e, the ln, so that we can evaluate this number here in our calculator. Obviously, this is going to be a little bit easier to see in an example. So let's do one. So we're going to solve these equations, and it doesn't matter which one you use when you do it. You can use log or ln. We pick those because those are the ones the calculator can evaluate. Notice we're going to need those here because we have a base 5, and we aren't going to be able to solve for this very easily. So I'm trying to get that exponent down. I don't want to take the logarithm yet, though, because my exponential term isn't by itself. For this, we have to have the exponential term by itself. So you're still going to get that x term alone. We can subtract 8 in order to do that. That means we've got 5x equals 12 minus 8, which is 4. This is where we are stuck. We were stuck before and we had to test values for x. We don't have to do that anymore. What you're going to do right now is take the log of both sides, or the ln. It doesn't matter. You'll end up with the same answer, and you can test that out for yourself if you want. Okay? So I'm going to take the log of both sides. I can do the same thing to both sides of an equation, and the equation will remain true, and that works with logarithms as well. Okay? So the equation hasn't changed except for the fact that I've taken the log of both sides. That means that this exponent can now drop down out front of this log and be multiplied by that log. So now I have x times log of 5 equals log of 4. Remember, log of 5 is just a number now. I can divide off by that number. And this is just a number over here. So x equals whatever that is when I plug it into my calculator. Actually plug that into your calculator right now. You should get about 0.8614. Okay, make sure you plug in log of 4, close those parentheses, and divide that by log of 5, and make sure you have those parentheses around each one of them. All right, let's try it again with this next one. Here our exponential term is 3 to the 2x, and it's being multiplied by 14. So we're going to divide off by 14 first because we have to, again, get the exponential term alone. That'll leave us with 3 to the 2x equals to 28 divided by 14. That simplifies nicely to be 2. This is where I need to drop that exponent down, and I can do so by taking logs because my exponential term is alone. So I log both sides. 3 to the 2x is what I log on the left-hand side, and 2 is what I log on the right-hand side. Again, you could also use the ln function here. That drops the entire exponent, whatever is in the exponent, no matter how complicated, it drops it down out front. So now I'm solving 2x times log of what the base is, which is 3, equals log of 2. Now currently on my left-hand side here, x is being multiplied by both 2 and log of 3. So I can divide off by both of those at the same time on both sides. The 2's will cancel, the log of 3's will cancel, and x will be equal to, plug this into your calculator. Anytime you have something more complicated, put parentheses around it. Now, things to note here, the 2's in no way cancel because that 2 is trapped inside of the log. Okay, you need to plug this entire expression into your calculator. Do that and see if you get my same answer. You should get 0.3155 when you plug that into your calculator. That's a rounded number, okay? I kind of like to round out to about 4 decimal places when I'm doing this to get the most accuracy. Okay, so the key here is now we can solve for variables in our exponent, but we have to get that exponential term alone first. So we're going to go back to 3 examples that we've worked on throughout this chapter 5 and see if we can't now solve exactly for that missing variable that was in the exponent. Okay, so here's an example, and this is just good review of chapter 5 as well. So this first one says you invest $5,000 in an account compounding annually at 3.2% interest. How long will it take for your money to double? Okay, so let's set up the equation first. We're talking about compounding annually. So here we're looking at that P equals P naught times 1 plus R over N to the NT formula, and we need to plug in what we know. We invest $5,000, so you should have put a $5,000 in for P naught. We have 1 plus a rate of 3.2%, so 0.032. We're compounding annually, so N is just 1. And we're looking for T, right? We want to know how long it will take for our money to double. So what should our output be if our money is doubling? $5,000 will double to be $10,000. We want to know how long it takes for that $5,000 to double to $10,000. Okay, so let's start doing a little simplifying so we can see what we're actually trying to solve here. 10,000 then equals 5,000 times our base is 1 plus 0.032 over 1. That's just 1.032. And our exponent is 1 times t, and so that's just t. So our exponential term here is our base 1.032 to the exponent of t, which is our variable. We can now solve for that variable, but the first thing we've got to do is get that exponential term alone. The 5,000 is being multiplied by our exponential term, so we're going to divide by 5,000 on each side. When we divide that 5,000 off, 10,000 over 5,000 will simplify to that doubling of 2. That's what we want equal to 1.032 to the t. We're going to find our doubling time for this equation, our exact doubling time. Now, we're solving for our variable, which is trapped in the exponent. This is the point in time where we can take the log of both sides and solve for it. Log of 2 equals log of 1.032 to the t. That's what's going to drop out front, that exponent, and we'll have log of 2 equals log of, that exponent drops out front, right? So write down that t first. T times log of 1.032. Log of 1.032, try and make yourself remember that's just a number, and it's being multiplied by my variable now. And since it's being multiplied now, I can just divide it off. I divide it off on both sides, and when I plug this into my calculator, log of 2 divided by log of 1.032, you should get a t value of about 22 years. We're looking for time. This interest rate here is always our annual interest rate, so that's our time unit, which is going to be in terms of years. Okay. Let's try another one. This next one says we're going to invest $2,000 in an account compounding continuously at 3.2%. We want to know how long it will take to have $3,000. So the first thing you want to realize here is we're compounding continuously. That means we have the formula P equals P naught times e to the RT. We're starting out with $2,000, so we plug our 2,000 in. The E is just a constant. We're doing it at a rate of 3.2%, so 0.032. And T is what we're looking for. We want to know how long it will take to do what? To get $3,000, so that will be our output. Our exponential term here now is e to the 3.032t. We need to get that term alone, so we're going to divide off what that e is being multiplied by, divide off by 2,000 on each side. Now, do not round as you're going. So 3,000 over 2,000 simplifies down to 3 over 2. That equals e to the 0.032t. Now here again, you could log on both sides, but we have a base e there, so I'm going to show you how ln works just the same, and also show you why I would ln here since it matches the base of my exponential term. So here we've got the ln of the left-hand side, 3 over 2, equals the ln of e to the 0.032t. And again, that exponent, the entire thing will drop out front. So the entire 0.032 times t all comes out front. We've got ln of 3 over 2, that's just a number, but we don't want to find it yet, is 0.032 times t, and then times the log that's left, times ln of e. Now plug this into your calculator and you'll see why ln works really well here. This part here equals 1, so we don't need it. Anything times 1 is just itself, and that's why it's a little bit simpler. So we really just have ln of 3 over 2 equals 0.032 to the t. If we would have taken the log of both sides, this just wouldn't have simplified away. Now all we have to do is divide both sides by what's being multiplied by the unknown t, and we've got it. Plug in ln of 3/2 and divide that by 0.032. Make sure you close this parenthesis on ln so you're dividing outside of that log. Okay, and you should get a t value of 12.67 approximately. And again, this is years because we're looking at interest rates, and interest rates are always given in terms of a yearly interest rate, unless otherwise stated. All right, so we're doing it, guys. We're solving for those variables that are in the exponents. We're figuring out those doubling times, or how long exactly it would take us to get an account balance that we wanted. All right, let's do one last example here. This one is about half-lives, okay? So we're doing an exponential decay function. We've got carbon-14, which is used to date archaeological samples. It has a half-life of 5,730 years. And if it now has 30% of its original carbon-14, we want to figure out how old the sample is. This is a lot like one that you worked on in your presentation question. So if you happen to get that one wrong, make sure you pay attention here so you understand how to set this up. So we're looking at the fact that we have a half-life of 5,730 years. Remember, we have that nice, so we know this is exponential decay, y equals c times a to the x. We're given that decay factor of a half in terms of so many years. So remember, if we have it in terms of so many time periods, we can divide off by that time period in our exponent in order to make this x in terms of just years instead of 5,730 year time periods, okay? You just need to divide off by it in your exponent. Now the question here is I want to know how long it takes to get somewhere, so x will in fact be my variable. So what should c and y be in this case? So you can think about an example. If the sample now has 30% of its original carbon-14, then it now has 30% of whatever we started with. Well, let's just keep this simple and say we started with a sample of one so many units, right? Or you can think about that one as we start with 100% and now we have 30% left. Okay? So we're really looking at here that 1 times anything is just itself. So this is really just 0.3 equals 1/2 to the x over 5,730. At this point, we're solving for x. We're solving for how many years it takes to get down to 30%. And we have our exponential term by itself. So we are just going to log or ln both sides of this equation. Log of 1/2 to the x over 5,730. Again, this entire exponent drops down out front. So this gives us log of 0.3 equals, oops, see if I can get that equal sign to look a little better there, equals x over 5,730. That's my entire exponent, which is then going to be multiplied by the log of the base that is left. So I need to do 2 things here now to solve for x. X is being divided by a number and multiplied by a number. Let's undo that multiplication first. Divide off that log of 1/2 first. Again, don't start rounding yet, so I would leave that alone. That's log of 0.3 over log of 1/2 or 0.5 equals x over 5,730. So we'll need to take that left-hand side times 5,730 in order to solve for x. This is now what you can plug into your calculator. Test it out. Make sure you get all your parentheses in the right place. That 5,730 is being multiplied out front, so it's just being multiplied. Let me make sure that looks correct. There you go. Okay, and plugging that in, you should get an x value here of 9,952, rounding to the nearest hundredth, 0.81. Now, go back to your problem to figure out the units here. X was in terms of years. So that's 9,952.81 years. That's how old the sample is if 30% of its carbon-14 is left. All right, you're going to get lots of good practice with this on the homework, but email me again if you have any questions. And that's our last lesson, so we're going to be looking at talking about the final next week. All right, let me know.